In this video, we'll be working on implicit differentiation. Let's jump right into example one and kind of explain what's going on with respect to that first example. So we're being asked to find dy dx by implicit differentiation. Part A, x squared y plus xy squared equals 3x. So the idea here is we are going to treat y as if it were a function of x. Now, you'll notice that we can't isolate y. We can't get y equal to a whole bunch of stuff with x's here, right? With addition, subtraction, multiplication, powers. We can't do it. We can't get y by itself. Or if we can, it's not going to be a simple method to get there, and it's not going to give us a simple result. So we're going to just treat y as though it's a function of x. And what you'll notice, let's just look at the y squared for a moment. If we were to take the derivative with respect to x, remember this symbol here is a command to take a derivative of what comes after with respect to x. So if we're going to take a derivative of y squared with respect to x, and we're thinking of y as being a function of x, you can imagine a sine x instead of the y, for example, you would have to use chain rule. So this would equal 2y to the first power, that's using the power rule, but then we'd have to multiply by the derivative of the inner function, which a moment ago I said imagine it's sine x, we would put the derivative of sine x. And so when we take this notation here, it's again a command to take the derivative of y with respect to x, and we just write that as dy dx. So this ends up being the derivative of the outer function, leaving the inside alone, whereas this is the derivative of the inner function, and that's chain rule. So that's the basic idea behind implicit differentiation. Let's actually do example 1a now. So we're going to take the derivative with respect to x of x squared y plus xy squared. And then we're also going to take the derivative with respect to x of 3x. Now, again, if we're going to treat y as a function of x, that means that what we have right here is a product of two functions. And here we also have a product of two functions. So we're going to have to use the product rule. So we're going to get the first function right there times the derivative of the second function, which is going to give us dy dx, plus the second function times the derivative of x squared with respect to x is 2x. So that right there gives us this derivative right here. Then we're going to add, using another product rule, we're going to get the first function times the derivative of the second, but again, y, think of it as a function of x. We would have to use chain rule and get dy dx, right? That's the derivative of just this piece here. We take the derivative of the outer function, the 2 comes down in front, we subtract 1 from the exponent, and then we multiply by the derivative of the inner function, which is dy dx. So there's the first times the derivative of the second, plus the second times the derivative of x is 1. And so there's the product rule on this right here. And finally, on the right-hand side, we're going to get the derivative of 3x, which is just 3. So now that we've gotten to this point, our goal is to isolate dy dx. And so we notice that we have a term involving dy dx here and a term involving dy dx there. So I'm going to put those next to each other. And we end up putting our terms without dy dx back here. Now, our goal is to isolate dy dx, so it really just becomes a bit of an algebra problem now. These terms will get subtracted to the other side of the equation. Now we'll factor out dy dx. And finally, we're going to isolate dy dx by dividing both sides by this quantity here. And we have it. This is the derivative of y with respect to x based on our original equation. We call this implicit differentiation because we're unable to get y by itself and take the derivative like we normally would. Or maybe we can get y by itself, but it's just too difficult or becomes too ugly for us to deal with. Let's look at part B. So with part B, we have these square roots, and we're going to need to take derivatives. So let's go ahead and first rewrite it as x plus y to the 1/2 power plus xy to the 1/2 power equals 6. And with this xy to the 1/2 power, it might be easier to rewrite it as x to the 1/2 power times y to the 1/2 power. So now we're going to take the derivative with respect to x of this whole side, and we'll do the same thing with the 6. Taking the derivative of x plus y to the 1/2 power with respect to x, we'll first use the power rule, bringing the half in front, subtracting 1 from the exponent, and then taking the derivative of the inner function, the derivative of x with respect to x is 1, plus the derivative of y with respect to x looks like this. Plus, now with this next part, we're going to have to use the product rule. So we have our first function times the derivative of the second function, dy dx, because y can be thought of as a function of x, plus the second function times the derivative of the first, and then the derivative of 6 is 0. So once again, we have this product here. Its derivative is all of this right here, using the product rule. So now we need to clean this up. We're going to isolate dy dx. And so we're going to need to distribute this quantity into the parentheses. We also have negative exponents all over the place, so let's go ahead and rewrite all those first. So there we've gotten rid of the negative exponents. Now we'll go ahead and distribute this here and here. Now we notice that these two terms both have dy dx. So we're going to keep them on this side of the equal sign, and we're going to factor out dy dx. And that's going to look something like this. Meanwhile, we have this piece here, this term, and this term here, neither of which have dy dx. So we're going to subtract those to the other side of the equal sign. Now, to get dy dx on its own, we need to divide by this quantity here on both sides. It's going to give us a bit of a mess, and then we'll clean it up afterwards. Next, we're going to clear all of these fractions in both the top and the bottom by multiplying by the LCD. We're going to multiply on top by 2x to the half, y to the half, times x plus y to the half. and do the same thing on the bottom. This quantity in green now will be distributed here, 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 and here, and we'll get a bunch of cancellation. So with our first multiplication right here, the 2x to the 1/2 will cancel, and we'll get a negative y to the 1/2 times y to the 1/2 gives us just y, and we have x plus y to the 1/2 power. Multiplying next here, we're going to get cancellation with the 2 and the x plus y to the 1/2, so we're just going to get x to the 1/2, y to the 1/2, and there's our numerator. Multiplying down here, we're going to get cancellation with the 2 and the x plus y to the 1/2, so we're left with x to the 1/2, y to the 1/2. And finally, multiplying here, we're going to get cancellation with the 2 and the y to the 1/2. So the 2 x's to the 1/2 will give us x to the first power when we multiply those together, and we'll get our x plus y to the 1/2 power. Now, we could rewrite this with square roots, and it would look something like this. Let's look at part C. So, just as before, we're going to take the derivative with respect to x of this entire side here, and also on this side. So notice right here, we're going to need to use a product rule. So we have our first function times the derivative of the second, but remember, y can be thought of as a function of x, and so we have to multiply by the derivative of the inner function, which looks like this. So there's the first times the derivative of the second, plus the second function times the derivative of the first, just that x, is 1. So that gives us the derivative of the green part using product rule. Plus the derivative of cosine, actually let's write minus, because the derivative of cosine is negative sine, and we have a 2y here. And then we have to take the derivative of 2y, which is going to be 2 dy dx. So that's the left-hand side. And then taking the derivative of cosine again is a negative sine y dy dx. So here we're noticing that we have dy dx in 3 different places, right? We've got this term, and this term. And we want to get all of those together. So let's go ahead and get all of our terms with dy dx on the left, and then this term here we'll subtract over and get it on the right-hand side of the equal sign. Now we'll factor out dy dx. And the last step is to divide by this entire quantity here to isolate dy dx, and then we'll be done. Example 2, if x times the quantity f of x cubed plus x times f of x equals 6, and f of 3 equals 1, find f prime of 3. So this is similar to the previous problems, except for here instead of y, we've got f of x. But we're still going to do implicit differentiation. So we're going to take the derivative with respect to x of each side. And we notice that we've got a product of two functions here and another product of two functions here. So we're going to be using the product rule twice. So we've got the first times the derivative of the second, and we have an inner function of f of x, so we have to multiply times the derivative of the inner function. Again, this is the chain rule applied to this function right here. So there's the first times the derivative of the second plus the second times the derivative of the first. So there's the product rule on this first part right here. Now we apply the product rule again. The first times the derivative of the second plus the second times the derivative of the first, and that's the product rule applied here in green, equals the derivative of a constant is 0. Now we'll go ahead and group the terms containing f prime of x. So we have 3x f of x squared times f prime of x plus x f prime of x. And then we'll subtract over these two terms that don't have an f prime. So we get negative f of x minus f of x cubed. Now we factor out an f prime of x. And finally, we divide by this quantity to get f prime on its own. Finally, we evaluate this derivative at 3. Using the given information, f of 3 is 1, so that's going to go here, here, and here. And that's it. Example 3. For the curve given by x to the third plus y to the third equals 6xy, first they want us to find dy dx. So again, we start off by taking the derivative with respect to x of each side of this equation. So we get 3x squared plus 3y squared dy dx equals, the 6 is a constant multiple, so I'm just going to put it on the outside of parentheses, and then we'll go ahead and take the derivative of xy using the product rule. So we have the first times the derivative of the second plus the second times the derivative of the first is just 1. Now we'll go ahead and distribute the 6 and then get all the terms with dy dx on one side of the equal sign and all the terms that don't have dy dx on the other side. Now factor out dy dx. Divide both sides by this factor here to isolate dy dx. And finally, we can factor out a 3 from the numerator and denominator and then cancel. That's going to leave us with a 2y minus x squared over y squared minus 2x. Next, we're going to find the tangent line to the curve at the point 3, 3. So that's just a matter of taking dy dx from our previous step and evaluating it at x equals 3 and y equals 3. Then we take this slope and the point 3, 3 and find the equation of the tangent line. Part C, at what points on the curve is the tangent line horizontal or vertical? Let's start with the horizontal tangents. The tangent lines are going to be horizontal when the derivative is equal to 0. Let's simplify this expression to isolate y. Multiply both sides by y squared minus 2x. So we have y equals 1/2 x squared. So each horizontal tangent line will occur at xy pairs on the curve where y is equal to 1/2 x squared. But since these points have to be on the curve, the points where we have these horizontal tangent lines, that means we can substitute this quantity here into the y values for the original equation. Again, all we've done here is we've taken 1/2 x squared, plugged it in here, and plugged it in here. Now we solve this equation. So that means that either 1/8 x to the third is equal to 0, or x to the third minus 16 is equal to 0. Here, x will be 0. Here we have x to the third is equal to 16. So that means x is equal to 16 to the 1/3 power. Next, we need to find the corresponding y values. We can do that quickly by plugging in 0 for x and 16 to the 1/3 power for x in this equation here. When we plug in 0, we get 0, 0. Now we find the corresponding y for 16 to the 1/3 power. Let's first notice that 16 to the 1/3 power is the same as 2 to the 4th to the 1/3 power, which is the same as 2 to the 4/3 power. Now when we plug it into our y equals 1/2 x squared, we get y equals 1/2, and we have this quantity squared. Simplifying that, we have 1/2, we have 2 to the 8/3 power, and we can cancel by thinking of our 2 in the denominator as being 2 to the 3/3 power, which will give us 2 to the 5/3 power. So we have found the 2 points where this curve has horizontal tangent lines. Let's look at the vertical tangents. So the vertical tangents will happen wherever the derivative is undefined. In other words, we're going to take the denominator of the derivative and set it equal to 0. Just as we did previously, let's go ahead and isolate one of the variables. In this case, x is easier to isolate. Now we'll go ahead and plug in 1/2 y squared for x in the original equation. So just as we did in the horizontal tangents case, we're taking our 1/2 y squared and we plugged it in for x in the original equation. Now we solve for y. So we're probably noticing at this point that we're getting the exact same equation, but our x's and y's are switched. In other words, compare what you have here with what we had here. So solving this is going to give us the same results, except for y will be 0 and y will be 16 to the 1/3 power. Also, since this equation and this equation are identical with the x's and y's switched, that simply means that the x's and y's are going to switch in our final result. So instead of going through all the work that we just did for the horizontal tangents, it's pretty clear that we'll get 0, 0 again for our vertical tangent, and we'll get 2 to the 5/3, 2 to the 4/3 as another location for our vertical tangents. Let's look at the graph real quick, just to see how we did. So here's the graph of x to the third plus y to the third equals 6xy. Notice that we have a horizontal tangent line at a y value of 2 to the 5/3, just as we had found, and also a horizontal tangent line at y equals 0. Similarly, we found that we had a vertical tangent line at x equals 2 to the 5/3, and also a vertical tangent line at x equals 0. Two curves are called orthogonal if at each point of intersection their tangent lines are perpendicular. So if we have one curve and a second curve where the green curve has a tangent line at this point of intersection, maybe like this, and the purple curve has a tangent line at the point of intersection, maybe like that. If these tangent lines are perpendicular, then we say that the curves are orthogonal at this point. However, if the two curves are orthogonal at all of the points of intersection, then we say that the curves are orthogonal. So in example 4, they want us to show that the curves are orthogonal, given the curves x squared minus y squared equals 5 and 4x squared plus 9y squared equals 72. So what we're going to do here is we're first going to find the points of intersection. And then at each point of intersection, we need to check the slopes of the tangent lines of each curve, and then from that determine whether the tangent lines would be perpendicular. So we can go ahead and isolate x here, and then plug it in to the second equation for x, and then solve for y. So we get that y is equal to plus or minus 2. By plugging in plus or minus 2 here, we'll have x squared minus 4 is equal to 5. That means x squared is equal to 9. So x is equal to plus or minus 3. This means that we have points of intersection at 3, 2, negative 3, 2, negative 3, negative 2, and 3, negative 2. Next, we'll find dy dx for each curve. To do this, we'll have to do implicit differentiation again. So we're taking the derivative with respect to x, implicit differentiation. For the first equation, we get 2x minus 2y dy dx is equal to 0. Solving for dy dx. We get x over y. So the slopes of the tangents for the first curve, so I'm going to notate that with m sub tan 1, is x over y. Now we do the same sort of thing with the second curve. So the slopes of the tangent lines to the second curve are negative 4x over 9y. The last step here is to plug in each of our points and see what the slopes are for each curve. So for example, at 3, 2, the slope of tan 1 is simply the x value, which is 3, over the y value. And the slope of tan 2 is equal to negative 4 times the x value, so that's a negative 12, and 9 times the y value is 18, and that reduces down to negative 2 over 3. And so if we remember back from algebra, if we have two slopes that are reciprocals and opposite signs, that means that the two lines are perpendicular. Now we just need to repeat this at each of the remaining points. So after plugging in each of these points into dy dx for each curve, we see that in each case, the slopes are opposite signs and reciprocals. So in each case, the tangent lines at the points of intersection are perpendicular. Therefore, we can say that the curves given in this problem are orthogonal. Go ahead and do the similar problems that follow.